In a world of change, the night sky has come to signify all that is eternal. Seasons may pass, civilizations may rise and fall, but the stars still traverse the heavens each night in a timeless celestial procession. So steady is the light of the stars that the constellations we see each night are the same ones our ancestors gazed upon thousands of years ago. And each individual star could shine for millions or billions of years more. The stars and galaxies convey the impression that the things we see in the universe are permanent and unchanging, at least over the course of a human lifetime. But that's not always the case. One of the most astonishing phenomena in the night sky is so fleeting that most people have never seen it, even though it's very common and can easily be found without a telescope. For generations, the Aurora Borealis, or Northern Lights, have enchanted those lucky enough to see them. With their bright colors and strange, wavering movements, the auroras seem to be alive with a supernatural energy, a perception that arises again and again in stories from the past. In North America, for example, the Algonquin people explained them as the light reflected from the campfire of the Creator. While to the Vikings of Scandinavia, they were the Valkyrie, supernatural beings who accompanied fallen warriors on their way to meet the gods. And in many northern cultures, they are simply regarded as the spirits of the ancestors, dancing in the sky. But it was the astronomer Galileo in the 1600s who first named these events Aurora, after the Roman goddess of the dawn. Galileo incorrectly speculated that auroras were reflections of the sun's rays. But he did get one thing right. It is the sun that is ultimately responsible for the aurora. It would take 3 more centuries before Christian Birkeland, a Norwegian scientist, hit upon the correct explanation. The aurora, it turns out, are the result of billions of microscopic mid-air collisions. Starting at around 250 kilometers above Earth's surface, electrically charged particles from the sun collide with the oxygen and nitrogen atoms and molecules in our atmosphere. The gases are energized by these collisions, giving off a colorful glow. The different colors relate to the height, energy level, and type of gas. For example, oxygen can glow both red and green, while energized nitrogen can produce a blue or crimson color, or sometimes both at once, which makes the aurora seem purple. The solar particles responsible for all this energizing can be seen most vividly during a solar eclipse. As the moon slips in front of the sun, the blazing light of the sun's surface is temporarily blocked. As the sky goes dark, a feathery glow appears around the silhouette of the moon. This is the solar corona, a region where particles blasted off the sun's surface are heated to extreme temperatures and eventually driven outward into space. As they travel, the solar particles form an invisible current called the solar wind, which blows past the planets of our solar system on its way to the stars. As the solar wind flows past Earth, some of the particles are captured by our planet's magnetic field, which is generated deep inside Earth's core. Like tiny compass needles, they follow the lines of magnetic force heading down to our planet. The magnetic field lines converge near the north and south poles. The aurora they produce are mostly seen far from the equator, closer to the Arctic and Antarctic regions of our planet.
Discover the past with exclusive history documentaries and ad-free podcasts presented by world-renowned historians, all from History Hit. Watch them on your smart TV or on the go with your mobile device. Download the app now to explore everything, from the wonders of ancient Pompeii and the mystery of the princes in the tower to the life of Anne Boleyn and D-Day. Sign up via the link in the description.
Sometimes auroras are dazzling and brilliant, and other times they do not appear at all. The secret to why auroras are sometimes spectacular and sometimes scarce lies again with the sun. The more active the sun, the more potent the solar wind, and the more beautiful the auroras. Like Earth, the sun has its own magnetic field, but the sun's is more powerful and it originates within the hot plasma deep in the interior. The most obvious signs of the sun's magnetism are sunspots, dark patches that appear where lines of magnetic force have broken through the surface. Regions associated with sunspots can be incredibly dynamic, sometimes spawning massive explosions called solar flares, which can release more energy than the detonation of 1 million nuclear bombs. An active sun is also more prone to coronal mass ejections, magnetized bubbles that can grow within the sun's corona and ultimately burst outward, sending billions of tons of energized particles racing through space, turning the steady flow of the solar wind into the equivalent of a hurricane. If such an event happens, within hours, high-speed particles are battering Earth's magnetic field. Down on the ground, the effect is often a spectacular display of aurora. But there are other effects. Violent fluctuations in the Earth's magnetic field can overload power lines and cause blackouts. Because of their potential to disrupt technology on Earth, solar storms are the subject of intense study. That means the aurora have now stepped out of myth and legend to become part of a larger space laboratory, helping us to understand the sun and its influence on our planet. The aurora may be a phenomenon of our atmosphere, but it is directly connected to forces at work far off in outer space. Perhaps it's fitting, then, that we have to go to space to understand it best. Like a delicate sculpture suspended in silent grace, the International Space Station sails over our planet. The station is humanity's most ambitious outpost. It lies only a few hundred kilometers above Earth's surface, yet it is our beachhead into the infinite vastness beyond. With the station, we now have a perpetual eye on our planet from above, a way to see Earth in all its glory, including oceans, continents, and our best views yet of the Earth's colorful aurora. Until the arrival of spaceflight, we really had only one place from which to view the aurora, down on the ground. That's changed now, and so has our understanding of what's really going on when the sky is on fire with northern lights. When it comes to the aurora, it turns out that space is the place to get the big picture.
4, 3, 2, 1, 0.
In 2007, NASA's Themis mission probed the forces that can turn a calm aurora at the poles into an all-sky light show with potentially paralyzing consequences for our technology. 5 microsatellites measured electric and magnetic fields in space, as well as the flow of solar particles during an aurora. At the same time, an array of 20 ground-based stations in Canada and Alaska took wide-angle shots of the aurora while making magnetic measurements. Themis revealed that the energy contained in just one solar storm is equivalent to that released in a powerful earthquake. The mission also found invisible strands of Earth's magnetic field dangling 40,000 kilometers out into space. Called magnetic ropes, these ephemeral fields capture solar wind particles, briefly tying the Sun and Earth together until the ropes unwind and dissipate. A parallel project, Europe's cluster mission, involves 4 identical satellites orbiting the planet in formation. Their goal is to provide a 3-dimensional picture of how the solar wind interacts with the Earth's magnetic field and produces aurora. Like mapping an electromagnetic landscape, Cluster is helping determine exactly how particles that originate at the Sun gradually find their way down into our atmosphere. These studies from space remind us that auroras are a planet-wide phenomenon, and they should arise wherever the same 3 ingredients occur anywhere in our solar system. Those ingredients include the flow of particles from the solar wind, a planet with a strong magnetic field, and a dense atmosphere for the solar particles to collide with. The planet with the strongest magnetic field in our solar system is Jupiter, a giant ball of gas so large all of the other planets would fit inside it. Jupiter would seem like a prime spot to search for auroras beyond Earth. Even at a distance 5 times farther from the Sun than Earth, Jupiter's intense magnetic field is strong enough to pull in the solar wind. Io, the closest of Jupiter's large moons, sports its own magnetic field. Gas in its atmosphere glows, causing a small aurora of its own. This field affects particles caught in Jupiter's magnetic web, funneling them toward a specific spot in the giant planet's atmosphere, creating a bright spot in the aurora that changes position with Io. Fainter spots in Jupiter's auroras are believed to be the footprints of Ganymede and Europa, 2 more of Jupiter's large moons. Saturn is another gas giant in the solar system with auroras. First captured in one of the Hubble Space Telescope's early images, these auroras are now monitored by the Cassini spacecraft currently orbiting Saturn. Hubble and Cassini both found auroral ovals around Saturn's poles, but glowing in ultraviolet light. Later, Cassini found a whole new set of auroras glowing in infrared. This aurora, unlike any other before seen, covers the pole rather than crowning it like a glowing ring. The ability to explore the other planets in our solar system has shown us that auroras are not a phenomena unique to Earth. Anywhere where a moon or planet with a gaseous atmosphere and a strong magnetic field is exposed to the relentless tides of the solar wind, we should expect to see something like the Northern Lights. And now, with technology on our side, it's possible to enjoy these dancing lights as never before. The Aurora Borealis have inspired our stories and filled our dreams since long before the beginning of recorded history. Yet our efforts to adequately record and study these colorful, moving lights in all their ethereal beauty have always fallen short, until now. Today, the advent of digital photography makes it possible to capture the faint and ever-changing light from the auroras. Now, backyard stargazers around the world are putting these tools to use and showing us what until now only a few were lucky enough to witness. An aurora we see from the ground is part of a larger structure in the form of two large ovals centered on the north and south magnetic poles. To see auroras regularly, you have to be under one of these auroral ovals, or at least close enough to catch a glimpse. That means people living in the far north or south have the best chance to see auroras on a regular basis. When there are more particles flowing toward Earth, the ovals expand, covering a larger area and making auroras visible nearer the equator than usual. Observers at latitudes closer to the equator will only see the highest auroras, which appear as a reddish glow in the direction of the poles. In some cases, auroras hang like curtains above the Earth. This is because Earth's magnetic field traps particles from the solar wind and channels them almost straight down. They cannot wander away from the field lines, so from a distance, we see them as sheets of light. Some of the most spectacular auroras of all are those that occur when these shifting curtains of light are directly overhead. They create the effect of radiating lines of moving light, pulsing and emanating from a central point. Such displays are breathtaking, and they ensure that no matter how well we come to understand auroras, we will never cease to be filled with wonder when we see them. When you stop and think about it, no other process in nature so directly connects something that's happening deep beneath our feet in the core of the planet with something that's happening inside a star, our sun. But there's also another way that the aurora may connect us here on Earth to the larger universe that we're a part of. Because they are a product of Earth's magnetic field, auroras are a visible sign our planet is largely protected from the bombardment of particle radiation that would otherwise be raining down on us from space. By deflecting and channeling many of these particles toward the north and south poles, the magnetic field acts as a shield, making the Earth's surface safe for life as we know it. Although today we are far from being able to observe other Earths directly, astronomers are now beginning to test the idea that we might someday be able to detect the energy of an auroral display underway on another world beyond our solar system. If such a detection could be made, it would come with some big implications. It would allow us to distinguish between a planet like Earth and similarly sized planets like Venus, which has no magnetic field and is completely inhospitable. In fact, the presence of auroras on another planet would be our cue to look for signs of life. Mysterious and beautiful, intriguingly complex, we have now come to realize that the auroras that light up our night sky are also a colorful calling card that advertises our existence. Perhaps the auroras of another world will one day help lead us to our first meaningful contact with other conscious beings in the universe, and point the way to a cosmos full of light and life. Engages us with both its unending vastness and its rich diversity. The farther we look, the more we discover, and the more we realize how much there is yet to understand about the cosmos that surrounds us. The challenge for astronomers is that our view only extends so far. Our technology allows us access to a finite part of an infinite reality. Physically, we are bound to the Earth and the nearby worlds of our solar system. With our observatories, we can only see the light that happens to come our way from the stars and galaxies. How then can we hope to explore the parts of the universe we can't reach and can't see? Fortunately, there is a way. One that doesn't just enhance our senses, but enhances our ability to imagine the universe in a virtual way. Once, there was only one way to explore the distant universe, through the eyepiece of a telescope. But times have changed. Astronomers can now turn to their supercomputers to conjure up representations and simulations of what goes on in reality in order to see and understand reality better. Along the way, they've created something that's close to a new kind of art, the art of cosmic visualization. As a starting point, computers can help transport us to where we can have a new and better vantage point on places we've already explored. One such place is the Moon. Humans have not set foot on its desolate surface since 1972. Since then, many robotic spacecraft have orbited our satellite, taking countless images and sending back a torrent of topographic and mineral data. Most recently, scientists have obtained some of their best views of the Moon with NASA's Lunar Reconnaissance Orbiter, LRO for short. LRO carries a powerful camera as well as an altimeter, which bounces laser light off the Moon's surface and measures the time it takes to reflect back to the spacecraft. Together, this information can be assembled in a computer to provide a three-dimensional perspective of lunar craters and mountains, bringing us much closer to the surface than the spacecraft actually traveled. What is most astonishing about this particular flyover is that, although it looks very realistic, no astronaut has ever seen this part of the Moon. And scientists are interested in finding out more. These views are not simply aesthetic choices. They are created to help planetary scientists better understand the complex history of the Moon's ancient surface and identify future landing sites where rovers or astronauts may one day unearth a deeper understanding of our nearest neighbor in space. After the Moon, humanity's next step into the great beyond could well be Mars. No planet apart from our own has been the subject of such intense scrutiny and the destination of so many robotic missions. In recent years, it seems an entire fleet of spacecraft has descended on Mars, either roving over its terrain or imaging its surface from orbit. Like its lunar counterpart, the Mars Reconnaissance Orbiter studies the planet from high above. But this computer-simulated flyover, created with data from the spacecraft, makes it feel like we're staring out of the window of a Martian airplane. Traveling to Mars would present the biggest challenge humans have yet faced in space, and it is still far from routine for the robots blazing a trail here. Lots of data is key to planning an effective exploration. Even for an unmanned rover, it is crucial for researchers to know what is waiting for their vehicle before it sets down on the planet's surface. Here, information from Mars Reconnaissance Orbiter has been turned into an in-depth tour of Gale Crater, now selected as the landing site for Curiosity, the next rover to be sent to Mars. The crater reveals an intriguing landscape. Sections of its floor are covered with ancient sediments that may have been deposited long ago by flowing water. At the center of the crater is a towering mountain, 5 kilometers high. How it came to be there is unknown, but its layers of rock were laid down at a time when Mars may have been warm and wet enough to support life. Researchers hope views like this will help them chart an optimal surface route for Curiosity's challenging mission. In a completely different way, Astronomers have used computers to obtain a three-dimensional view of the Orion Nebula, one of the nearest and most spectacular star-forming regions in our galaxy. Here, the computer allows us to travel many times faster than the speed of light, flying around the cluster of bright stars at the heart of the nebula. These stars illuminate the hydrogen and other gases within the nebula, making them glow. They also drive back the gas with a strong stellar wind, which creates a hollow space inside the nebula and exposes the embryos of new solar systems in the midst of formation. Such views are both artistic and scientifically accurate, but they merely scratch the surface. The real power of computers involves not just exploring new landscapes, but in revealing the hidden forces at work in shaping our universe. The roots of astronomy lie in our attempts to keep time. Patient sky watchers once used the stars to divide the night. They tracked the sun's yearly trip through the stars by watching the constellations appearing out of the sunset and fading into the dawn. Now, the arrival of powerful computers is allowing astronomers to deal with time in a new way. The real power of supercomputers in astronomy is not simply to show us what the universe might look like in places that are too hard for us to get to. It's to show us how things change over vast timescales that we could barely comprehend, let alone experience. In that way, a computer can be like a cosmic clock. Just set it running and see what kind of solar system or galaxy or universe takes shape. Astronomers have long thought our solar system formed out of a disk of debris that swirled around the newborn sun 4.5 billion years ago. When we peer with telescopes at star-forming regions elsewhere in our galaxy, we can find evidence of disks around other young stars. But how exactly did it happen here? And how did it lead to the family of planets we recognize as our solar system, including one planet, Earth, that ended up in just the right place to support life? Because we can't go back in time to see how we got here, astronomers use the information gleaned from observing other stars to set up computer simulations of our solar system's formation. Such simulations offer a virtual laboratory to test detailed theories of what really happened. Astronomers have had some success modeling solar systems, but can we turn the clock back even farther to simulate the birth of galaxies? According to current theories, the galaxies we see today formed from smaller galaxies, created when the first stars died and left behind black holes that act like cosmic glue. The black holes came together, creating cores around which larger galaxies formed. As we see, galaxies did not form in isolation. Often, many formed in the same part of space, gathered in clusters and superclusters. In some cases, two galaxies may run into each other. This can be a gentle collision, a cosmic fender bender in which the vast distances between the stars in each galaxy means they pass right through each other, distorting only slightly due to their mutual attraction. In other instances, simulations show how celestial fireworks can occur, with galaxies smashing into each other, exploding, and recreating in a completely new form. As we look around the sky, we see many examples of interacting galaxies. And now, supercomputers are helping us turn time backwards to see how they got that way. Even our nearest galactic neighbors are in the process of interacting. The Andromeda Galaxy is 2.3 million light-years away. Through a telescope, it's also possible to see a smaller companion galaxy. Modeled here, with each star represented as a point, we see the two galaxies engage in a long, slow, gravitational waltz. According to this simulation, the dance leaves a big impression on both galaxies. But, as is usually the case, it is the smaller partner that is more obviously affected by the gravity of its larger neighbor. Our own Milky Way is smaller than Andromeda, and observations reveal that we are also on a collision course with this galactic monster. Flashing forward billions of years into the future, we see the fate of our own galaxy is to collide and ultimately to merge with Andromeda. Will this affect our planet? It's hard to imagine that it will not. By then, Earth will be into its old age and very likely no longer a habitable world for humans, or anything like us. But here, with the help of a computer, we can see how the future will play out far beyond the boundaries of our own experience. After centuries of scanning the skies with telescopes and decades of sending unmanned probes to other planets, we should know our own solar system pretty well. But we can't see everything. For example, we know the formation of our solar system should have spawned a zone of small icy bodies well beyond the orbit of Neptune. Pluto, discovered in 1929, may simply be one of the largest members of this group, collectively known as the Kuiper Belt. Since 1992, many dozens of Kuiper Belt objects have been discovered, and estimates suggest there could be up to 70,000 more. Now, a computer simulation can help show us how the Kuiper Belt may appear to an infrared telescope observing our solar system from a distance. It appears as a glowing ring because collisions within the belt create dust, which radiates a faint infrared light. A gap in the ring reveals the presence of a planet. In this case, Neptune. Scientists can also take the simulation backward in time to see how the Kuiper Belt is likely to have changed over billions of years. Eventually, it devolves back to a simple ring, exactly what's been found surrounding some other stars that are much younger than our Sun. The computer is our gateway to understanding the hidden influences at work in the cosmos. The ultimate hidden influence is the influence of dark matter. Discovered through its gravitational pull on stars and galaxies, dark matter gives off no light and is not directly observable by any other means. A lump of dark matter would pass through Earth like a ghost, since it does not interact with ordinary matter at all. Yet the dark matter in our universe outweighs normal matter by 5 to 6 times, and its gravitational pull has had a profound effect on the way the universe has evolved. Using computer simulations, we can now imagine what it would be like to fly through our own galaxy and experience it as though we were wearing dark matter glasses. The effect is something like driving through a snowstorm, but on a galactic scale. In this visualization, everything made of atoms, including stars and planets, have been rendered invisible. What we see is only dark matter, which the computer shows us forms in countless clumps that orbit around the galaxy's center. Over the course of our solar system's history, Earth may have flown through many of these clumps, but we would never know this. However, the presence of this dark matter guides how the stars move and shapes our galaxy. The effects of dark matter grow even more significant as we look to larger scales. For example, when we peer out to the universe over hundreds of millions of light years, we find the galaxies are not distributed randomly. Instead, we find there is a pattern to the way the galaxies are organized. Astronomers call it the cosmic web. Matter has tended to concentrate, and galaxies have tended to form in sheets and filaments, leaving surrounding voids or bubbles where matter is relatively scarce. What is the source of this cosmic web? With the help of supercomputers, astronomers have been able to determine the answer. When dark matter is added to the equations that show how the early universe took shape under the influence of gravity, it is the cosmic web that emerges. There's no question that the use of supercomputers has both broadened and deepened our knowledge of how the universe works, and that computer simulations have allowed us to travel through time and space in a virtual way so that our minds can go where our bodies cannot follow. The best part is this is just the beginning. Supercomputers are only getting faster and better, and that means the virtual universe that's opening up before our eyes is probably going to be even more imaginative and spectacular. Perhaps there's an even deeper insight we can glean from the new power of computers and the way they are being used to help us understand nature at the largest scale. What these simulations tell us is that the cosmos is inherently mathematical in nature. Whatever our universe is, and however it came to exist, it is governed by numbers and relationships that can be represented in a computer. The universe is not getting smaller or easier to understand, but with computers to aid us in our future explorations, we know that much, much more of it will now be within our grasp.